All right, so I want to do a really quick rundown of how to compute rotations using the method of virtual work. So what we're going to do is we're going to take the example that we did in class today, which just to recap, we were looking at this beam and we were looking at determining the rotations at point B using the method of virtual work. And we did the, we computed the virtual displacement, or we computed the displacement at B using the method of virtual work. So we did our real structural analysis, we did our virtual structural analysis, and we did the method of virtual work, but we hadn't quite finished it for rotation at B. So just recall that we had computed our real moment function, 18x minus 0.6x squared, that was valid from x equals 0 to x equals 30. Then we had also, we still have our E and I value for the flexural stiffness. Now here's the virtual structure, and what we need to do is, since we're determining the rotation at B, what we need to do is we need to apply a virtual moment. Okay, so what I'm going to do is I'm going to apply a unit moment right here. Now, what I've done is I've assumed the rotation, I've assumed the direction, and I've assumed that it is rotating in a clockwise fashion. Now, the reason for that is here's the beam, and let's put this up here. I'm thinking that the deflected shape of this beam is probably going to be something like that. So if I'm looking at this point, it's sort of like faced that way. So I'm thinking that like the rotation is going like that. Hence why I'm applying a clockwise moment. But in the end, it doesn't really matter, right? Because you just do the math, and if the answer is positive, that means your assumption is correct. So that's kind of the idea. All right. Now, if I sum moments, so let's make sure we're clear. This is point A, and this is point C. So if I sum moments at A, and I apply my moment, apply my equation of moment equilibrium, I get 1 like this, no moment arm, no distance because it's a concentrated moment, but then I have Cy, this reaction here, Cy, I have Cy at a moment arm from A of 30 feet. So 1 equals Cy times 30, or Cy is positive 1/30 or 1/30 up. So this is actually 1/30, okay? And if this is 1/30 up, then the sum of forces in the y direction says that AY is 1/30 down, okay? So maybe I'll put that down here. Sum of the forces in the y direction, AY is 1/30 down. Okay. So what I want to do is I want to draw the shear and moment diagrams just to sort of illustrate what's going on. So when we draw the shear diagram, what happens is I start out at 0, I go down to a 30th or a -30th, and then there's no change. And when I get here, there's no change. This is a concentrated moment, not a shear. So we just keep on trucking. So I'll put -1/30 here, but we just keep on trucking. And then we go back up to 0. So that is our shear diagram. Now, just for the sake of discussion, so we're going to compute the area of the shear diagram, and we're going to do this in 2 segments for a very specific reason. Of course, I left my phone on. My apologies. So here we have our area. So I'm going to take each segment. So I have 1/30 times 10. So this area is minus 1/3. And this area is going to be minus 2/3. Now I'm actually splitting it up for a reason, and you'll see why. Okay. So if I'm drawing the moment diagram, here's what's going on. Constant shear, linear moment to minus 1/3, but then right at this point, I have a jump. I have a jump of 1. And the jump has to be upwards, because if I look at the area under the shear diagram, if I sum the areas, I get -1. So I have to have a positive jump of 1. So this is 2/3. And then this -2/3 brings me back to 0. So this is my moment diagram. Okay, 2 linear functions. We still have 2 moment functions that we need to define, one from x equals 0 to x equals 10, one from x equals 10 to x equals 30, and I'm going to do that the same way I did it before. So for M1, the slope, so first off, let's write the slope. Now the slope of each of these is the value of the shear diagram, in which case is -1/30. Now M1, we have a slope of -1/30, and the point is 0, 0. So therefore, just -1/30 times x, no y-intercept. Valid from 0 to 10. Pretty straightforward. Linear function on the left. For the right, we have the slope of -1/30. Now, what I'm going to do is I'm going to do it the way I did it in class. I'm going to say that the point is 30, 0. Okay, and we're going to find something kind of interesting. So if you see what I did before, I did the y minus y1 where I did this. I'm going to do that here. I'm going to say y minus y1 equals slope x minus x1. And let's just carry it out. So y minus 0 equals -1/30 x minus 30. So y equals -1/30 x plus 1. So M2 is just 1 minus x over 30th, or minus x over 30 from 10 to 30. But the interesting thing is, what is the difference between M1 and M2? They're really the same function. The only thing is, if you take M1 and just shift it up 1, you get M2. But that makes sense because what did we do to the moment diagram? We shifted it up 1 because that was the moment we applied. So it all sort of makes sense in the end. Hopefully, when you look at your math and then look at the behavior, it should all sync up. So now what we're going to do is we're going to apply the principle of virtual work, so method of virtual work. And we're going to apply the same, principle. We're going to say that theta is the sum of our integrals. It's the same concept. Remember, we know what our E and I is. I can do better than that. So I'll rewrite them. E is 4,000. I is 6,000. Okay, so let's do the same thing we did before. So the range, okay, so the range for this one was 0 to 10, and from this one was 10 to 30. We have the little m functions, in which case little m was, so for here it's -x30, here it's 1 minus x over 30. Now we have our big M function. And then now we just evaluate the integral like this, and I like to keep them separate. So this one, if you chug this out, and again, I'll do this first one together just so that we all kind of see it. Let's see, calculator. Oh, wrong calculator. I need Casio. So I'll do this one together. So we'll put the little screen up here so it's kind of bigger. So we integrate. So we're doing a fraction negative x over 30, 18 times alpha x minus 18x minus 0.6x squared from 0 to 10. And we get minus 150. Okay, so minus 150. And so there's that one. And if you do the next one, so it's the same integral. So all we're doing is evaluating it. Well, it's largely the same integral. We're just evaluating it from 10 to 30, and our little m function changes. Big M stays the same. When you do that one, you end up getting positive 800. Okay, so therefore, the theta at B equals. So what do? We sum up the integrals. But we have to divide by EI. We got to incorporate that. So what we're going to do is we're going to take negative 150. Whoop, over EI plus 800 over EI and then because this is a rotation, we're going to multiply it by a new conversion factor, in this case 144 times 180 over pi. So all you have to do is chug that out, and when you chug it out, I'm actually going to do this one over here. I'm getting 0.223. So therefore, it was positive. Oh, hold on. 3 degrees. And we assumed that the rotation was this way, and we got a positive answer. So that's our answer. And what the heck? We've got a little bit of time. Let's just chug this out together and see if we're getting the same thing. So that's negative. So we will do that times that. And then this should be pi, which is shift pi. 0.223 degrees. So pretty straightforward. Not hard. You know, the hardest work is setting it up. Once you set it up, the actual calculations are pretty straightforward. Didn't mean to drag that away like that. Sorry about that. Oh, goodness. Move that. There we go. That's what I meant. So yeah, so I think you find this is pretty straightforward. With that, I'm going to stop this recording and upload this, and we will see you all on Friday.